Okay, yeah, I guess let's begin this week's Department of Statistics seminar series. So I'm very excited. I think we should all be very excited for this week for Professor Glenn Shafer talking to us from Rutgers. So I'm sure that most of the people in the audience will be familiar with his work. Perhaps you've seen one of the numerous books that he's written, and some of them even very recent, very exciting, and related to some of the conformal prediction stuff that we saw last week. So this algorithmic learning textbook. I would say that Professor Shafer is probably most known for his stuff with the Dempster-Shafer theory. And also a lot of his really nice work in foundations and philosophy of probability topics. And I've personally written a lot of his really well, beautifully written papers on history of probability topics and so on. So I definitely encourage students to visit his website and look at the numerous things that he's done over the course of his career. There's a lot of insight and perspective, I think, that can be gained from looking at things that he's done. And with that, I will turn over to Professor Shafer. So let me stop my share, and it's yours.
Well, that's wonderful. Thank you for that very gracious introduction. It makes me, feel that I wasn't just writing for the ether there. Somebody's been reading my papers. That's a great feeling. And I also, I'm delighted by this. 66 people. Okay, I'm delighted by this opportunity to tell about, I suppose, my most recent work. I am a very senior statistician, if you're willing to call me that. And so I would like to devote the rest of my career to, I claim that I want to devote the rest of my career to writing books about the history. Mm-hmm. This recent paper that I'm going to be telling you about today, the paper that, I read to the Royal Statistical Society last September, it's almost out, I think, in print. Well, it's available on their website, under their read papers. I've been telling myself for some time that's the last paper I'm ever going to publish. Somehow papers keep getting produced, so it's not.
Especially with students around all the time.
Excuse me?
Especially with students around all the time.
Yeah. So it's not quite working that way, but I think it's the most technical paper I ever planned to write. I'd like to do some more philosophical and historical things. So what's my title? In a little different title. The paper that I'm talking about was called Testing by Betting. And I chose today, it's the same topic, but I chose a little more explicit title. Some of the discussants of my paper at the Royal Statistical Society said, "Are you saying we have to get rid of p-values?" Well, I said, no, you can keep doing it, but I have something else you could do sometimes. But in this talk, I'm going to say, okay, let's just get rid of p-values. Let's replace them by betting outcomes. And the great advantage of this is that it's not just replacing p-values with betting outcomes, it's also replacing power with the target of our bets. And I'll show you how natural that is. And the advantage of that is that the betting outcome and the betting, what I call the betting score, and the betting target are really more closely related than p-value is with power. I think all of you who have some experience with statistics know that p-value and power don't really fit together, because p-value is not about a fixed level significance. And it's also not about a particular alternative. But power, to define power, you have to define both a particular alternative and you have to define a fixed level of significance, and p-value throws that out. So they don't always fit, and they kind of, you get some paradoxes, if you want to call them that, where you see the misfit, and I'll talk about some examples of that. But before I look at examples, I'll tell you about my book, I guess. That's the next slide. I'll tell you about the book that Vovk and I published in 2019. It's really a book of mathematics. And it says it's basing mathematical probability. It's basing the theory of probability. It's saying instead of using measure theory as a foundation for probability, let's use game theory as a foundation. So that makes it in, and it shows how you can do the mathematics that way. So it's really, this testing by betting is really used as a way of developing mathematical probability theory. There's not that much stat in this book. Well, there is, but it's kind of hidden. So my talk today is not going to be so much about what's in this book as it's about what's in my article on testing. There's lots of other, there's a lot of other working papers we have a website for this book, but it also has a lot of working papers. What's that? We're up to 57, I think 58. We have 58 working papers there. Goodness. So this book follows a earlier book that Vovk and I also published 20 years ago. So we've been working on this for 25 years. The one 25 years ago focused on proving the classical limit theorems, law of large numbers, central limit theorem, law of the iterated logarithm, and showing how we could be more constructive than measure theory. This new book does more abstract theory, because measure theoretic probability is really very abstract theory, and here we show how game theory probability can be equally abstract, but we also give more applications. So I hope you'll have a chance to look. I'm talking today about this mismatch between p-value and power, and then I'm going to jump into testing by betting. Let's see, what am I going to say about the mismatch? I only have 3 slides. The first slide is just a quotation. Eric Lehman, I'm sure some people here have heard the name Eric Lehman. Eric Lehman was my first statistics teacher. I didn't study statistics until graduate school, and the first course I sat in on was Eric Lehman teaching from his classical books, Testing Statistical Hypotheses. And back when I did it, he was still teaching from the first edition, published in 1959. So I was looking for some quotations, and I went back and looked at, Eric, can I call him Eric, or I would like to have counted him as a bit of a friend, though we didn't spend a lot of time together. He was everybody's friend. Went back and say, what did he do? I went back to see what he said about p-values. I remembered he had defined p-values in that book. So what is the name he gives them? He calls a p-value a critical level. Look what else he did. He says this p-value, what we now call a p-value, he says it gives an idea of how strongly the data contradict or support the hypothesis. Now, all of you have been following this recent controversy about p-values, and you know that a high p-value does not support the hypothesis. That's an error. That's an error, and we're telling people that, hey, if you know any statistics, you shouldn't do this. You should know better. Anybody that's teaching statistics should know better than that, and we are complaining that people don't know better. Well, Eric Lehman in 1959, Eric Lehman was 42 years old in 1959. He had been Jerzy Neyman's prize PhD student, best PhD student at Berkeley in the early 40s. And then he had taught some other places, and he'd come back to teach at Berkeley again. Eric got p-values wrong. Well, he wasn't real. P-values weren't really his thing. He was doing fixed significance testing, fixed level significance testing. But when he put a paragraph about p-values in the book, in the second edition, he took that or support out. But I thought it was a little bit sobering. that Eric got it wrong in that book that was like the Bible of testing hypotheses. Well, part of the point of that was that people had different names for p-values. Let's see what's happening to my my lost control here somehow. I can't get rid of. You can see my cursor.
Yeah, I can see it.
Yeah, somehow I'm having a hard time getting rid of my getting the. Oh, there it is. I probably okay. This next slide just talks about names for p-values. Part of the point is that p-values have been talked about for a long time. They go back to the early 19th century. Cournot called it the Antoine Augustin Cournot, the great philosopher of probability and stat in France after Laplace and Poisson, called it la probabilité de l'écart, the probability of the deviation. Carl Pearson called it the value of p. Kind of actually this p-value name got started kind of accidentally because Carl Pearson wrote down a formula that said p equals for his chi-square test. And then of course he had a formula that said p equals, so then in the rest of the paper he talked about the value of that p, called it the value of p. And all of his students after that called it the value of p. And when they said value of p, they knew what we were talking about. They were talking about that particular p. Well, not necessarily chi-squared, but whatever the test was, the probability of a deviation no larger or a probability of a deviation that small was the value of p. And Henri Fisher used that too. He didn't agree with Pearson and everything, but he took that name, the value of p, and he used it for his entire career until he died in the 1960s. So value of p. Who first turned it around and said, I mean, it's natural enough to turn it around and say p-value instead of value of p. The earliest example I can find is a geneticist named John W. MacArthur. I had never heard of him before I found this citation. That's the first one I can find. So some people used it, but it wasn't common. As I say, Eric Lehman tried out the term critical level. That didn't catch on. In the 1960s, Jerzy Neyman was calling it the significance probability. That was his name for p-value. You know, some of you might be surprised if you got, some people say, well, fixed level testing, that was Neyman. P-values, that was Fisher. That's a kind of common canned history. But no, it's not true. I mean, they both used both of those. And when Neyman did applications, he used p-values, but he called them significance probabilities. David Cox, he used the term observed level of significance. Some people say, of course, observed significance level. So there's all these names, but p-value after the late 1970s, it wasn't until the late 1970s it became popular. And now that's the popular, everybody says p-value. So the p-value assesses the evidence against a null hypothesis. How do we measure a study's potential for finding evidence against the null hypothesis? So we all know the answer to that. This just reviews the definition of power. Neyman and Pearson said we should take into account all the costs and benefits, and we should balance the probability of mistaken rejection with the probability of mistaken acceptance under a particular alternative. And given an alpha, we want to maximize 1 minus the probability of mistaken acceptance, and we'll call that the power. Does the power measure the potential for finding evidence for the alternative over the null? And yes, but only at level alpha. It doesn't really, if we're going to use p-values, power does not really tell us the sensitivity of the test. And people have thought about other things for doing that. In the 80s, there was some interest in calculating the expected p-value. Expected value of p-value. as an assessment of the sensitivity of the test. That's, yeah, it's not, that's not great either. Doesn't really escape from the problems, but it's interesting. Okay, testing by betting. What's my proposal? So let's establish some notation. Let's say we have a probability distribution. I'm going to call it a hypothesis. And we have a phenomenon or random variable. I'm going to call it y. This could be very general. Y doesn't have to be a real number. I'm calling it a random variable, but it could be anything for which we have a probability distribution. And how do we use a particular observation that the phenomenon comes out little y? How do we use that to test P? And the conventional thing we learn is that we choose a significance level, say 5%, and a rejection region. And we reject P if Y is in the rejection region, of 5% rejection region. So this already has a betting interpretation. And I imagine that many of you, probably most of you in this audience, teach statistics at some time or other, and you probably teach this topic. I would be interested in your feedback, how many of you think about or even talk to the students about the betting interpretation. So what is the betting interpretation? It is that the unlikeliness of rejection, if the hypothesis is true, corresponds to a bet you could make. You could put, I made these slides for a British audience, so instead of using dollars, I use pounds sterling. So you could put £1 on the rejection region, you'd only have to pay, and you would get $20 back if it happened at the odds stated by P. So part of the reason why that'd be surprising is you multiplied your money by 20. To multiply the money you risk by 20 is not really a reasonable thing to expect if you have a fair, if you're betting by the odds that are fair or correct in some sense. And in fact, betting against given odds and winning a lot of money, what better evidence could you have that the odds are bad? So I think that the idea that a small probability happening, an event happening with a small probability discredits the hypothesis. A lot of our intuition about that is based on the fact that we could make a lot of money if such an event happens. It's this betting interpretation. Who's my host? Is there a way of asking my question to the audience? Like, how many of you think about this or use it when you teach? I'm curious, I really am. This is a big audience of, I'm talking to one of the largest stat departments in the country, I think.
Yeah, so people can respond in the chat and I can maybe tally it up.
Okay, that would be good. That's great.
Raise hands for people who have done it instead.
Yeah, I can't see all 66 people at a time. I can't see all 66 people at a time.
There's also a polling feature.
Oh, is there? Can you run? I run that. That's under more.
I think the host is able to see it.
Okay, I'll let you see if you can do that, and I will proceed a bit. But the fixed level test does not measure the strength of the evidence. We all know to do that, we have the p-value, and the p-value, but that's more complicated because for the p-value, you got to have a test statistic, and the test statistic, well, what it does, it defines a test for every significance level. Actually, that quotation from Eric Lehman talks about this, that you have not just one test, but a family of tests. And then the p-value is the smallest alpha that rejects, and the smaller that is, the more evidence we think we have. Okay, that's fine. I think the logic is, there's some logic there. But my objection to it is it's too complicated. Well, but also my objection is it doesn't go together with the idea of power. But one objection is it's just complicated. Here is an alternative to the p-value. So my left-hand side here in black is what I already said. In blue, I have something I haven't said yet, and it's a new idea, a new way to, yeah, it's new, I guess. I mean, maybe some people actually had this idea 200 years ago, but as far as statistics, journals, and textbooks go, I think in the 21st century, it's a new idea. The idea is that you choose a bet that can pay different amounts. Instead of a bet that is like 0-1 or 0-20, either I lose my dollar or I make $20. Instead of that kind of bet, you choose a bet that can make different amount, that can pay different amounts. So I think of such a bet, well, it's just a non-negative random variable, a non-negative function of y. I don't have the words non-negative on this slide. There wasn't enough room, but I say it, non-negative. You choose a non-negative random variable s that has expected value 1 under the hypothesis. So the idea is you interpret these probabilities by saying that they are offers a bet. You can bet any random variable, you can buy any random variable for its expected value. And I'm saying I'll let you buy a non-negative random variable because that way you'll only be risking what you pay. So that's how much you risk. And for simplicity, let's make its price 1. So you're going to pay £1 sterling, and you're going to get back s of little y pounds sterling. And so the more you get back, the larger your evidence. I'm going to call it the betting score. So this is my alternative. This is what it talks about. This is the alternative to p-values. The alternative p-values is that you get to bet by buying a payoff that has different possible results, different possible betting outcomes. And the bigger that outcome, the more the null hypothesis is discredited. So I call this number s of little y the betting score. This is the factor by which you multiplied your money because you started with $1 and now you have s of y dollars and you only risked that initial $1. Now we don't have to insist on the, it's convenient to choose s so it has expected value 1, but we could have an s that had some other positive expected value, and then the betting score would be the ratio. Because it doesn't make any difference. We could multiply, if we multiply s by a constant, we multiply the expected value by a constant. So choosing the expected value to be 1 is just a convenience. The point is the bet, here's my vocabulary. S is the bet, and S of y is the betting score. So I distinguish between bet and betting score. That's like the random variable and the value, the outcome of the random variable. Bet versus betting score. Now where am I? Yeah. Likelihood ratio. What does that have to do with likelihood ratio? Well, it is a likelihood ratio. A betting score, in the way I just defined, is the same thing as a likelihood ratio. Think about it. I said a bet is a function of the random variable or the phenomena that we're trying to describe. It has to be non-negative and it has to have expected value 1. Well, expected value 1 means I'm going to assume everything is discrete. Keep this simple. This generalizes, but assume everything is discrete. So a bet is a function that's non-negative and expected value 1. That means if you multiply all the possible outcomes with all their probabilities and add them up, you get 1. But look, S times P is non-negative and its values add up to 1. That makes S times P a probability distribution. S times P is a probability distribution. Call it Q. That's our alternative. So this bet defines an alternative for which it is the likelihood ratio. That's the next line. If Q is equal to S times P, divide both sides by P. S is equal to Q over P. Well, sometimes we do likelihood ratio the other way. Sometimes we do null over alternative. For this talk, we're going to do alternative over null. That's the likelihood ratio. And we didn't start with the idea of a likelihood ratio. We just start with the idea of a bet, but it's a likelihood ratio. Now, a lot of people know this. Abraham Wald knew it. The people that, studied, people who studied Wald's sequential analysis, somewhere in their head, they know this. People that study martingales, they know this. But no, nobody thinks of this as a way of testing. Start with the idea of a bet as a test, and you get a likelihood ratio. Nobody says that, except, well, Glenn Shafer and his co-authors, and maybe more and more people that are interested in this way of doing things. So the conclusion is a bet against P defines an alternative Q, and the betting score S is the likelihood ratio Q over P. Are you any questions on this so far? I feel like I'm a little bit in the ether here. I'm not seeing my.
We do actually have some poll numbers. So 12 people answered yes, and 49 so far have answered no to your question about teaching or learning statistics using betting.
Wow. So, okay, so it's a minority do this. Interesting. But it's not unheard of. And that's about what, 20% said yes, who answered? But we now have 90 participants.
Yeah, that's exactly 20%. So
yeah. And half the people have not answered or not answered yet. Excellent. So that's very interesting. Okay, so where are we? We are that a betting score is the same thing as a likelihood ratio. As soon as you give a bet, that defines an alternative. That's the two things. Somehow, with a p-value or a test statistic, well, there are some spatial cases, right, where you have uniformly most powerful tests. But in general, a test statistic, the usual way of betting with a test statistic, usual way of testing with a test statistic, the test statistic does not uniquely define an alternative. But here, the bet, if we test by betting, as soon as we say the bet, we've got an alternative. Now, here's another question. Well, let me say, I should have added this slide first. So if we start with the alternative Q, then Q over P is a bet. So it's an if and only if. A bet is the same thing as a likelihood ratio. If we start with a bet, we get a likelihood ratio. It turns out to be a likelihood ratio. And if we start with a likelihood ratio, hey, it's a bet because it's non-negative and its expected value under the null. Do the calculation, the P's cancel out, we're summing the Q's, it's a probability distribution, so that adds up to 1. So likelihood ratio and bet are the same thing. But then that raises a question. Suppose instead of starting with a bet, we start with an alternative Q. Is it a good idea to use the bet Q over P? That wasn't Neyman and Pearson's idea. Neyman and Pearson had a different idea for what you should do, how you should test if you started with an alternative Q. But here it's sort of, there's a hint. Well, maybe we should think about Q over P as our bet if we want to think of Q as the alternative. So what are we doing if we do that? Why should we do that? Why should we do this instead of Neyman Pearson testing? So the answer is that maybe that we should do this if we want to do multiple testing. So if we want to do multiple testing, and by that, I'm not considering the situation, it says here that Kazia Dobzrika had raised hand. Does that mean she has a question?
Yeah, hi. I just have a quick question. You keep mentioning whether a bet is good or bad. Do you mean that in the sense that it's likely to win, or that it's useful in the testing sense, like we were talking about the analogy?
Let's see, okay, so I'm just saying, would this be a good bet to make? If we want to test P against the alternative Q, would this be a good bet to make? So I think I'm going to try to answer your question because there's different criteria, aren't there? Different
Mhm.
ways of a test being good. So we got to have some goal. We got to say, what is the goal? And I want to say that in a certain situation, well, different situations have different goals. So I want to distinguish between the scientific testing, and maybe instead of multiple testing, I should have written scientific testing. R.A. Fisher emphasized that if we're testing a scientific hypothesis, we don't test it just once. If we test it and find some evidence against it, somebody else should test it again, or maybe we should test it again. So when I say multiple testing, I don't mean you're going to test a whole bunch of things at the same time. I mean, the same hypothesis, you want to test one way and then test another way and so on. The scientific community wants to continue testing it until they've kind of beat it to death before they would be convinced. That is distinguished. That's distinguished from what Neyman and Pearson had in mind when they developed their theory, where they were thinking, in fact, Fisher made a big point of that. He said, Neyman and Pearson's theory is good if you're testing for industrial quality control, it's okay. If you're an assembly line and you're testing widgets, and the widget comes off the assembly line and you got to decide whether you're going to put it in the box to send to Walmart or not, or whether you're going to throw it back in the scrap pile, that's a decision. And that widget, if it gets thrown in the scrap pile, it's not going to be tested again. That's it. And if it gets put in the box at the Walmart, it's not going to be tested again either. It'll be up to the consumer to complain about it if it doesn't work right. So there's this distinction between decisions, one, where you're really making a decision that you go this way or you go that way, which is what Neyman Pearson really works for, and scientific testing. So I want to say, how should we think about scientific testing for testing by betting? So in scientific testing, we're going to do successive bets. So I propose the following principle when we're going to make one bet after another with successive tests of the same hypothesis. So the idea is we should start with unit capital and never risk more than that unit capital. So if I make my first bet and I multiply my money by 3, I start with $1 and I multiply my money by 3 the first time. That's pretty good evidence against the null hypothesis, but we better go further. We better check again. So now we do another study, new data, and we bet again. Well, how much can I bet then? I've got 3, I can bet 3. So I can keep betting with what I have so far. On the other hand, if my first bet, I make my first bet, I put $1 down and I only get 90 cents back, then the next time I don't have $1 to bet anymore. I can only bet 90 cents. So if you just never bet more, if you never bet more than you start with, you can just keep gambling, if you will, like a gambler that has a limited capital, can't borrow money, no line of credit, can't say, oh, I got a credit card. No, you put down the capital you start with, and that's all you can bet with. Can't risk more than that. Can't keep betting if you run out of money. That's the principle we're going to use for testing by betting. And I'm going to show you that if you're going to do that, then making the bet Q over P is the right thing to do. 2 participants raise their hand. Do we have some questions?
I have a question then in terms of this successive testing idea. Is your suggestion then that relative to people who might be doing multiple tests, doing some sort of combined p-value or combined confidence distribution to come up with evidence?
Hello? Did I lose you? What happened?
I apologize, my internet cut out for a moment.
Oh.
So instead of doing some type of combined confidence distribution or some type of combined p-value, then the accumulated winnings would be the evidence that would be considered across all of these tests that have been done in succession?
Yes. And we now have quite a bit of evidence, if you will. I'm not reporting on it today, but some of the work by my colleagues, Rudu Wang and Vladimir Vovk, have shown how much better that performs than combining p-values. So yes, that is the proposal, which I'm introducing here. Was there another question? Okay. So I think we've already said it, and our questioner there said it in a different way. But this puts it in symbols. You use Y1 to test P, getting a betting score S1, Y1. This is maybe you need to keep testing, so you observe Y2, it's got to be new data, and test P again. This time you obtain a betting score S2 of Y2. Now, the betting score is how much you multiply your money that time. So your initial capital of 1 became S1 of Y1 after the first bet, and that's all you have to invest in the second bet. So the meaning of the second score is you got to multiply your result from your first bet by the betting score from your second. So the amount of money you now have, you started with 1. This is how much you multiply your money the first time. This is how much you multiply to the second time. So your new betting score is the product. That's the idea. So what you want to do, if you're going to do many bets, what you want to do is maximize the product of the bets. You don't want to maximize their average. Not a good idea. You want to maximize their product. So if you want to maximize their product, what you actually want to maximize on each step, you want to maximize the expected value of the log of your score. And Gibbs inequality tells us that of all the bets we could make against P, the one that maximizes under the alternative, the logarithm of the score, is the likelihood ratio Q over P. This is what Gibbs inequality says. You can look Gibbs in, I'm not going to prove Gibbs inequality. You can look it up in Wikipedia. You can look it up in any book on information theory. The expected value under Q of the logarithm of a likelihood ratio, Q over P, is greater than or equal to the likelihood ratio where you substitute anything else for Q. That's what Gibbs inequality says. Not that hard to prove. But that's saying that this bet is the one that maximizes the expected value of the logarithm of your betting score under the alternative hypothesis. So, you know, that's not the only thing you could do. You could maximize the expected value of the betting score, individual betting score. Or you could maximize the probability that S is greater than or equal to 20. This is what Neyman Pearson said to do. Neyman and Pearson said, what you want to do is, this is the power under the alternative. You choose some level alpha, and you want to multiply your money by that amount or more. This is equivalent to the Neyman Pearson lemma. This is equivalent to Neyman and Pearson's conclusion, proven by the Neyman Pearson lemma, proves that if the Neyman Pearson lemma proves that if you want to a slight generalization of the Neyman Pearson lemma proves that if you want to maximize the probability of your betting score being bigger than or equal to 20, you should use the Neyman Pearson test with significance level 5%. But you can do these other things instead. This is not a very smart thing to do if you think about it. Maximizing, you look at examples, it's not a good idea. Kelly gave some examples of where you would do it. He had to really, do make up a bizarre story to come up with an idea where you want to maximize this. But this, you want to maximize this. He had a good explanation. This is a famous paper, Kelly's 1956 paper. It's what this guy is he's not known for anything else. John L. Kelly Jr. This paper is his fame. And he pointed out that if S is the product of successive factors, then you want to take the logarithm. You want to maximize the expected value of the logarithm because it's the logarithm that adds up and therefore obeys the law of large numbers. Right? The law of large numbers and the central limit theorem apply to sums. And if you're multiplying your capital, it's the logarithm that is adding. So to maximize the long run rate of growth, you want to maximize the logarithm. Now this is called, in gambling theory, this is called Kelly betting. If you know you have an advantage in betting, and you want to take advantage of that advantage repeatedly, you don't maximize what you can make on a single bet, you maximize this logarithm. This is also very important in information theory, in the version of finance theory taught by people that aren't finance theorists, but are management scientists. It's important in machine learning. This has been used. It's not been so well known in statistics, but I am saying it should be. I'm arguing for it. I think this is a key slide. Maybe I should pause for questions on it. Is there anything, is someone monitoring, is our host monitoring the chat? There's not a chat particularly, nobody's doing chat.
Yep, I'm looking at the chat. So far, people have been raising their hand and just asking.
I see, so you're watching them raise their hand? Okay. This is, if somebody doesn't understand what I just said, this slide is so key. But it's really saying why we should, if we're interested in the alternative Q, this is why we should make the bet Q over P. But I shall carry on. Now, the next important thing is the replacement of the idea of power. We're going to replace the idea of power with implied target. What is the implied target? Well, remember, the bet implies an alternative. You might not have the alternative in mind when you make the bet. You might not, well, if you're betting against somebody's probability distribution, you might not have a good idea. It might just be a hunch. It might be a seed. It might just be a whim. You'd say, I don't know, really, I don't know. I don't really know this subject better than the guy that made this probability prediction, but I can try something. But it turns out when you try something, that defines an alternative. So how well can you expect to do with your bet? Well, if that's the alternative, then you would expect to do that well, but you need to translate the logarithmic scale back to the original scale, so you take the exponent. So this is, in a sense, the implied target of your bet. So the idea is you could use that implied target to evaluate the test in advance. Now, people who test with the conventional way, not in stat departments, but in many, many applied fields. I've been teaching in a business school for 30 years. Is that right? Yeah, I've been teaching in business schools for 30 years. And in the last 25 years or 20 years, I've been in more than 30 years, gosh. Anyway, for many decades, I've been in an accounting department, and I've been watching people they never talk about power. They don't talk about power. What's their excuse? Well, their excuse is they don't know what alternative is reasonable. They've dodged that. But here you can't dodge it. As soon as you give your test, you've identified an alternative. And you may say, well, I don't take Q seriously. I just made this is just a whim. But Q is the test. Q is the alternative for which your test is optimal. So if this implied target is not big for the optimal alternative for your test, the editor shouldn't publish that paper. But if this implied alternative is large and Q is substantively a reasonable alternative, then you've got a good study before you've seen the results. Because either way, it's going to tell you something. Because it's going to be a likelihood ratio. So you don't have to get a significant result, quote unquote, to publish it. You shouldn't have to. You should be able to say, you should be able to take the paper to the editor, but take the proposal to the editor before you see the data and say, this is my test. It has a high implied target, which is like having a high power. And Q is reasonable. Everybody in my field would agree Q is reasonable. So, hey, this is a publishable paper, no matter what the results are of the study. So that's my argument for replacing power with this implied target. And as I said at the beginning, here, whereas power doesn't really go together with p-value, this idea of betting and implied target of the bet do go together. So here's the way this is what a study should look like. Okay, what is the phenomenon that you're studying? What is the null hypothesis, the probability distribution for it? What is a bet? That produces an implied alternative, and that produces an implied target. This is all in the design of the study before you see the data. You see the data, you get the actual Y, you get the betting score. That's the simple story of how you design and market and perform your statistical test. So that's the main theory I want to cover, and I have some classical examples. Does anybody have questions about the theory that I've looked at so far? I'm just refreshing my memory about what I have here afterwards. Okay. You're a very easygoing audience. In some fields where I speak, I get a lot more interruptions. Okay. So I'm going to use some very simple examples. Only a single observation from a null distribution. And the null and the alternative are going to have the same standard deviation. They're going to differ only in their mean. So in a sense, these are toy examples, but I want to remind you, and I got that objection. When I gave this to the Royal Statistical Society, or some of my referees thought, oh, these are just toy examples, they aren't real. And come on, these are, this is kind of these are the examples of statistical work. No, they aren't the thing, they're 200 years old. So they aren't, they don't get a publication today, but they are the examples, the most widely used statistical test for the past 200 plus years. 200 years is the difference between two proportions. You use the normal approximation, you got a normal distribution. And you get the same picture when the test statistic is the average of n observations. Here I'm only talking about a single observation, but that's a sufficient statistic. The picture would be the same if you talked about n observations. So the issues here in these examples arise in almost any statistical test. So these are not toy examples or special examples. They are the examples of the problems of statistical testing. So the first one, Andrew Gelman and his co-author John Carlin, in their widely read paper about ways of solving the replication crisis that will not work. they make the remark that the main issue with the replication crisis is results that are statistically and practically significant, but hopelessly contaminated with noise. And to explain what they mean, they give this example. This example is from their paper. Your null is that the observation is normal with mean 0, standard deviation 10. Alternative is the same thing except mean 1. And then the observation is 30. So it's wildly significant. If the actual alternative is, if the reasonable alternative is that the mean is 1, then this is also practically significant. But the noise is overwhelming. And you know that this is a very extreme observation, not only for the null, but also for the alternative. So
about 10 minutes remaining.
Okay. So according to our authority, this is the main problem in the crisis of replication. So what do we do here? The p-value is very small, we know that. The test doesn't have much power, 6%. So we have a mismatch between power and p-value. P-value looks great, but it has no power. The implied target is 1.005. That means you might hope to multiply your money. You might hope to make 1/2 of 1% on your money. Not a good implied target, so that agrees with the power. No power. The betting score is 1.34. That agrees with, unlike the p-value, the betting score is in line with the implied target. Unlike the clash between power and p-value, we don't have a clash here. The power and the implied target both agree the study is worthless, but Neyman and Pearson is rejecting because, not Neyman and Pearson, Fisher rejects with a low p-value, while the betting score sees that there's not much evidence. The likelihood ratio is just 1.3. So I can give 2 other examples, I guess. I can read. Okay, let me just say what the examples are. Instead of going through them, I'll take a little time to say some other things. Second example is a 5% test that has high power, but borderline outcome, even though the likelihood ratio favors the null. So here's the example. You got a high power. If you have standard deviation 10 and the alternative is 37, a 5% test is going to have high power. But 16.5 is going to be a borderline result. If you got a one-sided 5% test, you're going to reject. But on the other hand, it's actually closer to the null than it is to the alternative, so it doesn't make sense to reject. And the likelihood ratio will tell you that. The likelihood ratio will favor the null. So again, the betting, this is not going to look paradoxical if you use the betting approach. Third example, where a high p-value is interpreted as the evidence for the null. You can say only stupid people do this. Only those people that didn't hear what we were teaching, but hey, Eric Lehman did this in 1959, and was still doing it when I took his course, I guess. So I can talk about warranties. This approach gives us a different way of interpreting confidence intervals. We can come back to that. And do we have a question period after the next 5 minutes?
Yeah, there's a question period for about 10 minutes after 4. Okay,
so, but after after 4 o'clock, there's a question period.
Yeah, and then there's an extra session where some other people have signed up to meet.
Okay. Well, let me leave aside then. I have this section called warranties, which are really confidence intervals. So the point is this testing by betting, you can also get confidence intervals. And I give them a new name because we have a new rationale for them, but they actually aren't anything different. They're just confidence intervals. It's the same because you use a fixed level. And if you take a fixed level, then it doesn't matter whether you're doing my kind of bet, or whether you're doing a test statistic, either way, you're talking about a 5% region. So the warranties is just another name for confidence intervals, and I won't spend time talking about notation for that. But I want to talk about another topic. I want to talk about testing other things besides statistical models. And my idea here is, hey, we have an example here for broadening, using the expertise of statisticians in a wider world, because we are now being inundated with probabilities that are not based on statistical models. We have people giving us probabilities for how the elections are going to come out. We have people giving us weather forecasts. We have financial analysts that are giving us probabilities and estimates. We have neural networks that can produce probabilities. A neural network is a statistical model only in a very, it's a stretch to call it a statistical model. And the physical models that produce weather forecasts, I don't know. I don't think you can call them statistical models in any sense. The forecast could be a probability. It could be an estimate, like for the size of a dividend, or the amount it's going to snow, or how much wind there's going to be. And every forecast could be on a different topic. But my point here is this idea of testing by betting apply equally to all these situations. So if we start, if statisticians were to decide that they were experts in testing by betting and not just in p-values, maybe that my rhetoric here, excuse my rhetoric, statisticians are experts about a lot of things. But if we emphasize that we understand testing by betting, we would really broaden our expertise in the eyes of the world. I mean, everybody has got their phone in their pocket looking at the weather forecast. At least I'm here in the mountains in New York State, teaching at Rutgers remotely. Every day, the question is, how much more snow are we going to get? And when are we going to get it? So this is, the testing by betting can be used here too. So as an example, I gave Nate Silver's forecast for the Democratic nomination. Some of you may have noticed, have seen this, or some of you may know at least about the website 538.com. I think, I don't know who owns it now. It has had various owners. For a while, I think it was the New York Times, and then it was ESPN, and I think they belong to somebody else now. But anyway, it's always been run by Nate Silver, and he has a good staff, and Nate Silver calls himself a Bayesian statistician. But he's using a model that has a lot more than Bayes in it. He has a forecasting model. And when it came to the Democratic nomination, he tells us that he started running his model on the 5th of November, but he started publishing it early January. So when he started publishing it, he was giving about a, 40% chance for Biden to be the nominee. And who was in Sanders, he was giving about a 25% chance. And then he had like 10% chances for Harris and for Buttigieg and for, I think, Bloomberg. I'm forgetting who those people were. Maybe Amy Klobuchar was in there. But then look how they changed, Bloomberg went suddenly up to 60% and then down to 0 in a day. And that was the same time when Sanders went way down and when Biden did this thing from, Biden went down from his 40% to 10%. And then suddenly in like 2 days or something, he was up to nearly 100%. We all, if you're in the USA, you probably followed this where suddenly Biden was a nominee. What do these probabilities mean? Are they right? are they good probabilities? Is Nate Silver a good probability forecaster? How would you evaluate how Nate Silver is doing? What possible way is there? I mean, he's given, there was only one outcome. You can't say, were his 50% forecasts right 50% of the time? Were they calibrated? Let's see, do I have I'm almost done.
Yeah, just a couple minutes.
Okay, so I wanted to tell a story about a paper I rejected once when I was an associate editor of JAZA, but you can ask me about that in the question period.
Yeah, that'll be perfect actually for the question section.
But all I'll say here is, look, you can bet. Every day you could, he's got a probability distribution here. You could take any expected value of that probability distribution. You could bet on the age of the nominee. You know all these people's ages. You could bet on the age of the nominee by his probabilities given average age, given expected value for the age of the nominee. You could buy that age of the nominee. And every day you could buy something and then you could sell it back to him the next day and buy something else. So you could, as he changes, you could bet against his changes. And maybe you could make a lot of money if you know something he doesn't know, or if you just think he's overconfident about his high probabilities or whatever. If you think he's spreading the probabilities out too much, you can find some way to bet against him and see if you can make money. So you can also do that with weather forecasts. That's my story. So that's 4 o'clock. So thank you very much for your wonderful attention.
Yep, great, wonderful talk. I guess we can open it up if there are any quick questions now. And also you can write a question in the chat and I can ask the question. So maybe one question to get us started a little bit. Do you think that statistical inference in practice, so like explaining p-values, do you think that the broader community that uses statistics would get interpretations of p-values incorrect less often if we taught from a betting perspective?
I think your question means if we replaced p-values with betting scores.
Yes, you're right. Right. Yes, exactly.
Would they get confused less?
Yeah.
I actually do think that's true. I think people understand betting already before you teach them. I think they understand betting very well. I may have some slides saying that, but people understand betting against somebody. You put your money where your mouth is, and if you make a lot of money they would put a lot of information into it, and some things that seem like paradoxes or some things that sound like paradoxes or errors when you're talking about p-values are not such errors when you're talking about betting, because when you evaluate somebody's betting success, you take into account what you know or believe about their knowledge and skill. So if I'm betting against somebody who is very good, like if I'm betting against the National Weather Service and I do very well, people are going to hesitate. I'm going to have to keep doing very well a long time. But on the other hand, they may think I'm onto something. If I'm betting against somebody who doesn't know very much and I know a lot, and everybody recognizes I'm betting against somebody that doesn't know as much as I do, then my lack of success may show that all my knowledge is not much use for predicting that. Mm-hmm. So there's a lot of reasoning people would add in based on what they know about the predictor and the opponent that's betting. So I think people understand betting, and they understand that, I think they understand that I might be betting against something, and the fact that I don't make money is just because I don't know anything. Mm-hmm. So they wouldn't over-interpret my inability to make money by betting.
I see. Yeah, it's a very interesting perspective. We do have a comment or a question in the chat. Someone is requesting to hear the JASA story from when you were the associate editor.
Let's see, how did that go? The guy I won't name the name, and actually I can't remember the name, a very interesting statistician. And eventually he published his idea in a book. He was a Bayesian. And his idea, I was an editor of JAWSA I wasn't an associate. Steve, this was way back in the 80s. Steve Sigler got me to be editor for JAWSA. And after a year or two, after a couple of years, I resigned because I was so frustrated. I was rejecting the very best papers. I was young and I thought I had to go along with what the referees said. And all the interesting papers I was rejecting. And I was publishing stuff I didn't think was very interesting, so I quit it. But one of the interesting papers I rejected, the guy says, look, Bayesians are always calibrated. Always calibrated. He said, let's say that a Bayesian gives you a probability distribution. And you look at the you get for a probability distribution for a random variable. And you take that probability distribution and you divide it into quartiles. You look at the median and the 25 and 75% quartile, percentage points. So you have four quartiles. And you say, well, how often? He said he's predicted, the Bayesian has predicted probability 1/4 for each of those. How many of his predictions are right? 1/4 of them. Exactly right. 1/4 of his, you look at his predictions of 1/4, he's going probably 1/4 to each of those quartiles. And 1 out of 4 of his predictions is right. Okay, what about his 50% predictions? You look at the bottom 50%, you look at the top 50%, you look at the bottom quarter plus the top quarter, you look at the middle ones, there's 4 of them. Is that right, or is there 6 of them? Anyway, you look and see how many of those 50% predictions are right. Half of them are right. So the Bayesian is always calibrated. Doesn't matter what he says, he's calibrated. Wonderful to be a Bayesian. That was his paper. Hey, he was serious. He's a Bayesian. He was serious. You could have taken it as a joke. I should have insisted on publishing it. I should have told the editor, we should publish this. It's a great joke. But instead he published it in his book.
Yeah, it's a really interesting story.
Actually, I can tell you, this was many years ago. The guy is Frank Ladd.
Okay. Okay, so there are a few other questions in the chat, but I think that these would be a little bit longer of a discussion. So I think that this would be a good place to end for the formal seminar part of the talk, and then get into more of these in detail questions during the discussion part. So thank you very much.
Well, thank you. I appreciate the wonderful attention you guys have given to this talk.
Okay, so I guess let me stop.